Today we're going to be looking at Alan Eustace's world record skydive and using it to learn all about the layers of the atmosphere.
In order to reach 135,908 feet, Alan needed to use a weather balloon.
Not just any balloon, but a rather giant balloon. As a matter of fact, it grew to 11 million cubic feet. But you don't really have any perspective on how big that really is.
You may have noticed we're standing outside of a stadium. This is Nationals Park, home to the Washington Nationals baseball team.
The 2018 Major League Baseball All-Star Game was played right inside there.
The stadium can hold over 41,000 people.
Alan's balloon that he used was not just big. It wasn't huge, but it was enormous.
In fact, when fully inflated, this entire stadium could have fit inside.
Today we're going to be learning the science behind how that balloon got so big and the layers of the atmosphere.
This is STEM in 30.
Hi, I'm Marty.
And I'm Beth.
Today on STEM in 30, we're going to be learning all about the layers of the atmosphere.
And to do that, we'll be taking a look at Alan Eustace's record-breaking skydive.
He set the free fall record when he jumped from over 25 miles up.
Oh my gosh!
I
Wow!
We are joined by some middle school friends. What are you all working on?
We're experimenting with a vacuum pump.
Wow, we actually got a chance to do some of these same experiments that you're doing with astronauts.
Go ahead, pull that off.
Oh! I want to eat it. No,
You want to eat it?
Yeah. Oh, that looks disgusting.
Let me see that.
So you all saw that Alan Eustace used a weather balloon to get way up into the atmosphere. We're going to learn a little bit of the science behind why that worked.
Does anyone know why he used a weather balloon and not an airplane?
Because an airplane can't fly that high?
Exactly right. So he had to use a weather balloon. All right, so we've got our red balloon here. Let's put that in there.
Oh, this is gonna be.
Okay, so
Years.
are you
Before we hit the pump, what do you guys think's going to happen now?
It's gonna expand and blow up. It's gonna blow up. It's gonna pop.
All right, let's see.
Let's see.
Whoa. I'm scared.
Look
I'm
at that.
scared. I'm scared.
That is so cool. All right. So what's happening is we've sucked all the air out of that vacuum pump, and the balloon has higher pressure inside and lower pressure outside, so it expanded. The exact same thing happened with Alan Eustace's balloon that he wore for the world record skydive.
All right, why don't you take that out and let's see what happens.
Whoa! Whoa! Back to normal.
We had some students here at the National Air and Space Museum over the summer build their own weather balloon and launch it into the stratosphere. Let's take it away.
We are going to be launching a weather balloon into space.
In aviation, one of the important things is understanding how the atmosphere changes as you go higher. A weather balloon is a nice, quick way to get a glimpse of the atmosphere.
Before the launch, we had to find the altitude of the balloon launch, how long it's going to take, where it's going to land, all of that tracking information. So I had to call and file a NOTAM and tell them all the information about our balloon launch.
And what direction is it going?
Northeast.
I wanted to be a pilot, and also I wanted to try something new because I've never done this before, and I think it's good for me to experience new things. When you blow up the balloon with helium, I'm supposed to hold one of the quarters down just in case so the balloon does not fly away.
In the payload box, it read temperature, pressure, humidity, altitude.
We put this GoPro camera in this styrofoam box. And then after the balloon was filled up, everybody came together. We let it go, and it was launched up into the atmosphere.
3, 2, 1!
Our balloon went really high up in space, and you could see all the clouds, and you could see North America. We could see the outer blue lining of the atmosphere. Seeing the Earth as a whole for a first time on the balloon that we launched was such a thrilling experience.
So one of the things they found out is that once it hits the stratosphere, there's a layer that actually the temperature gets warmer. So that was one of the big questions the girls had to figure out, was why did it get warmer as it went higher instead of just getting colder.
We have moved to a different part of the museum, and we are going to create a scale model of the layers of the atmosphere. When I was teaching, I used to do this in my class all the time, and we'd tape 6 or 7 sheets of paper together to make our layer model.
6 or 7 sheets of paper. Here at the National Air and Space Museum, we supersized it, so we have got a really big model of the layers of the atmosphere.
And to help us learn about those layers today, we brought in meteorologist Chris Strong. Chris, thanks for talking with us.
Great to be here.
Now, we've got all of these lines on here. Are those lines at exactly 9 miles or 60 miles?
The atmosphere is a lot like the ocean, and it's always moving, always tumbling and bubbling. So as the seasons change, as the Earth rotates, revolves around the sun, all these things, the atmosphere is always kind of wavering. So these lines are like waves on the ocean. They're always changing at different heights.
But why is the bottom layer so small?
Well, because gravity is pulling down the atmosphere from above, so all of the atmosphere is getting pulled down to the surface by the gravity of the Earth, and what it does is it crushes everything down, and the place down at the bottom where it's weighing the most from all the atmosphere being above it, it really crushes it into a smaller layer.
All right, so for this next part, I need a volunteer. All right, let's have you come over here. Now I've got a quiz for you. You can ask your friends for some help, okay? Where on this model of the layers of the atmosphere do you think the International Space Station orbits the Earth? Do you have a guess? Go talk to your friends for a second and see if you can come up with how high you think it should go.
I think it's low orbit. I go with the ionosphere or ionosphere.
All right, come on back over. We're gonna have you pull on this string and raise this up until you think it gets to the right spot.
And you guys can give her hints.
Give her hints, tell her where to go. Higher, lower.
Higher. Keep going.
Just a little bit more.
Higher.
Just a little bit more.
Just a little bit more. Stop.
Ooh, you guys think it's right there, the difference between the thermosphere and the ionosphere? That is a great, great guess. You're a little too high. Let's bring it back down a little bit. Let's bring it back down a little bit to right about there. That's about 250 miles above the Earth. A little lower than you guys thought, wasn't it?
Yeah.
All right, now we've got another quiz. I'm going to need 2 more volunteers for this one. You hold this. Come stand right here by me. All right, let's have you 2 gentlemen come over here. All right, now we have the Aurora Borealis. Chris, tell us about the aurora.
So the aurora is radiation from the sun that streams out in all directions through space, but as it hits the Earth, as it interacts with the magnetism in the atmosphere around Earth, it causes the molecules in the Earth to really start vibrating in it and speeding up, and that causes them to emit light, and that's what the aurora is.
Yeah.
Awesome
Very pretty.
stuff. All right, so what we want you all to do is figure out where on this model the aurora happens, and you guys help them out.
Okay, where do you think
Go
it
ahead.
is?
Hold it up there and see where you think it goes.
Stratosphere.
All right, that's a great guess, but it actually happens a little higher. Go higher and we'll tell you when to stop. Keep going.
Keep going.
Keep going. Keep going. A little higher, and stop right in there. All right, that's where the aurora happens. Check out this video taken from the International Space Station by the astronauts on board of the Aurora Borealis from above. Absolutely amazing stuff. Now what we're going to do is we're going to zoom in on the bottom 2 layers. let's first take our space station and get it out of the way. Ryan, cut her down. There we go. All right, now it is time to take this top layer off and zoom in on the bottom 2 layers. Ryan, give us a little help here. And now you can see we have zoomed in on the bottom 2 layers and made them much, much larger on this scale model.
So now we're gonna place some other stuff. Who wants to help out? Come on up.
So we've got our model mountain here. So this one's pretty easy. It starts at the ground, okay? So go ahead and place that on our model here. All right,
Okay,
so
do you
let's go ahead and tape the bottom down there. All right, so over 5 miles tall for Mount Everest. That's pretty amazing, isn't it? All right, you can head back over there. We need another volunteer. All right, how about you in the back? Come here, yeah, come here.
I have an airplane. Where do you think airplanes fly?
So you guys help her out.
Higher, there, right there. Yeah, right there.
Good guess. It's a little higher than that, just a little bit. It's up about 6 miles.
I was about to say the S.
So it's up about 6 miles, so higher than Mount Everest. Pretty cool, huh?
Okay. Okay, we need one more volunteer.
All right, how about you? Come on over here. And this is my favorite one that we're going to do today. Come on over here. This is a thunderstorm. All right?
Okay.
And Chris is going to tell us about thunderstorms. Chris, where does weather happen?
All the weather happens in the lowest layer of the atmosphere, the troposphere. So all the water vapor, a lot of the content of the atmosphere is actually in this lowest layer that we live in.
All right,
Okay.
so take our thunderstorm, and I'm going to give you a hint. The top of this is flat. Where do you think it might go? Help her out.
Higher.
Keep going.
Higher. Right there. Right there.
All right, let's scoot it over just a little bit. Right. Chris, what are we seeing here?
So when the atmosphere is boiling and bubbling and clouds are bubbling up into the atmosphere and growing and getting taller and taller, what they hit this black line, they hit this ceiling. And what that is where temperature stops falling as you get higher up in the atmosphere, but it starts getting warmer as you go up. And that change in temperature is what these thunderstorms run into. And they basically hit it just like a glass ceiling and start spreading out into an anvil.
So you're telling me that we can go outside and see a thunderstorm off in the distance and really see the layer between the troposphere and the stratosphere.
Yeah, exactly, which is tens of thousands of feet up in the sky.
That's incredible. We need one more volunteer. And we're going to take a lot of help on this. How about you? Come on over. Now today we're talking about the world record skydive, okay? So we've got Alan Eustace in his, I'll give you a hint, spacesuit here. Take your string, and you guys help him out. Raise this up to where you think he jumped to make the world record skydive. Help him out, guys. Stop there. Who thinks higher? Who thinks lower? Who thinks it's perfect? All right, I see some that's higher, and they're correct, so keep going a little higher. Right about there. Alan Eustace jumped from over 25 miles up, and he broke the speed of sound with his body on the way down.
Wait, how?
We got a chance actually to talk to the engineer who helped build this suit, and he told us all about why it was so important that they know all about these layers of the atmosphere. Let's check this out.
I'm joined by Jared Leidig, who is one of the lead engineers on this suit that Alan Eustace wore to break the world record skydive. Jared, thanks for talking with us.
Thanks so much. It's great to be here.
When you designed this suit, did you have to think about the atmosphere?
Yeah, understanding the different layers of the atmosphere and how the atmosphere is built was super critical to understanding how this suit needed to be designed. So right at sea level, the air is really thick and it's relatively warm. The first layer of the atmosphere, called the troposphere, is delineated by temperature. So as you go higher and higher, the temperature gets colder and colder. The air also gets thinner and thinner. That happens all the way till where you hit what we call the tropopause. That's the coldest part of the lower atmosphere. Above that point, you get into the stratosphere, where the temperatures are rising and the air is continuing to get more and more thin. So that creates some really unique challenges for a suit like this, because at the beginning part of the ascent, it's all about dealing with cold. The coldest temperature we saw in this program was negative 108 degrees Fahrenheit. The stratosphere average is about negative 70 degrees Fahrenheit. So it's very cold. But above that point, the air starts to get really thin. So there's no air to pull heat away from the suit or the system, and the temperatures are also rising. So you cross through this point that we started calling the human sort of equilibrium zone, the human thermal equilibrium zone, where the temperatures are kind of perfect. And you don't need to add heat to the suit in order for a person in a suit to be a good temperature. But then above that, you start getting to the point where it's too hot, where there's no air to pull heat away, the temperatures are going up, and it starts being too warm in a suit. So understanding this, that the temperature kind of goes down and down and down until this point, and then it starts going up, and that the pressure is going down and down and down and down all the way until you get to space where there's no pressure left, is really critical to understanding how you would need to design a suit like this.
So some of those things that you learned in middle school really applied to designing this suit.
Absolutely. The atmospheric layers and where the first layer stops and what defines that layer and what the next layer is all about were the centerpiece to the very early stages of this design.
Awesome. Thanks for talking with us.
Yep.
If you want to learn more about Jared, head on over to our Facebook page. Not only is he a very talented engineer, he's also an incredibly talented musician. You may have heard the term into thin air, but actually air has mass.
This is an air Zuka, and it's a great example of air having mass. You pull this back and it shoots air across the room. That's how you saw Beth's hair flip up. This thing would be worthless in the vacuum of space.
I'd like to put you in the vacuum of space. Can we do some experiments now?
Sure.
We're going to talk about density. You want to tell us a little bit about density in the atmosphere?
Sure, so the most dense layer of the atmosphere is the one that we all live in down here in the troposphere. And there's a lot of molecules, which is great because there's a lot of air for us to breathe. But as you get higher and higher up, the density gets less and less molecules up there. So we'll talk about that.
Yeah, so let's take a look. We have some water that we've put food coloring in, and I put it into here. And Isabella, would you put some of this oil into the water for me? Good job. Now, what do you notice is happening?
All these, every color separated.
Okay. Why don't you give it a stir here? Stir up the oil and the water, and we've mixed it up. Okay, stop. Take the straw out. The oil has floated up to the top, and the water's still on the bottom. Chris, why is this happening?
Because the water is more dense than the oil. So the water, no matter how much you shake it up, stir it up, the water is always going to sink to the bottom and the oil is going to rise to the top.
We have more than 2 layers of an atmosphere, though.
Yes, we do.
Okay.
We have more layers to add on here.
Yeah, let's try some more layers. We've got Josh. Do you want to come up and help me? Now, for this, we've already put the first layer in. This is honey. All right, so we've got some honey in here. Okay. Now we've got corn syrup. Corn syrup is less dense than honey. Pour it straight in and let's see what happens. All right, let's try some dish soap. Pour that straight.
Nice and slow.
Nice and slow right in the middle.
Look at that, it just comes right back up to the top.
Okay, so we've got some dish soap. Put that down. We've got, that's separating out pretty nicely. We still got the honey down there and then the corn syrup and the dish soap. So let's try water that has food coloring in it. So pour that in nice. Got a little foamy.
Like a rainbow.
It does look like a rainbow. Look at that. Where's the water? The water's sitting on top of that because the soap is more dense. All right, we've got oil here, so pour that in there.
Nice and slow.
Nice and slow.
Look at that, it's going all the way down into that second to bottom layer and then coming right back up.
Okay, so let's take a look. You guys want to count these off with me? How many layers we've got?
1, 2, 3, 4, 5.
We've got 5 layers, just like the atmosphere, right?
Now we know that Alan Eustace wore this suit behind us to break that world record skydive.
We had a chance actually to talk to Alan Eustace about what he saw going up and then coming back down. Check this out. I'm joined by Alan Eustace, stratospheric explorer and the holder of the world record skydive. Alan, thank you so much for being here today.
My pleasure.
Tell us a little bit about your rise into the stratosphere.
So the only way to get up to these very high levels is a balloon. Planes don't even fly that high. So we had a balloon, we got it, we filled it up with helium. We launched it, so you start out at the ground and you're looking down and from this height, and you see these little pebbles, and then you're released, and I would start this very slow ascent. And the atmosphere down there is very thick, but as you go higher and higher, the atmosphere gets thinner and thinner. And you're in the troposphere to start with, and you go up past this layer called the tropopause, and that starts the stratosphere. And that continues to go up, and now I'm going up in the stratosphere, and you reach this really cool level, 66,000 feet about, which is Armstrong's line. And at that level, if you don't have a spacesuit on, the boiling point of water is 98.6 degrees. So your blood would literally boil away at that. The ozone layer is actually up a little bit above that. So you go through these layers you've heard about in school, and you continue up, and then you get up to the upper levels of the stratosphere, and that's where the balloon reached its peak, and that's where I started my jump.
What's the view like up there?
Stunning. Stunning. I think the thing that's most amazing about it is the atmosphere is very thin, and when you're going up, you actually go above our atmosphere. I was above 99.7% of the atmosphere, so I'm looking down at our atmosphere. I'm looking at the darkness of space. I'm looking at this thin atmosphere. I can see the curvature of the Earth. I can see whole states below me. And it's just an amazing view. And the thing that surprised me the most is I kind of expected our atmosphere to be kind of, dark blue, and then slowly get to light blue and then black. But it's not like that. There's all these intermediate layers, lacy, beautiful layers in our atmosphere that you probably can only see from above, and it was special.
Okay, tell us about coming back down.
So as soon as you're released, they do a countdown, 5, 4, 3, 2, 1. And of course they're looking before that at the area that I'm over, and is that a good place to potentially land? And once they decide that, then I'm released. And I'm in a position where I'm set to be able to go down, and instead of falling straight down like that, I start to do this turn. And then I go upside down, which isn't a problem because of the way we designed the system. But for the first time, I actually got to see the balloon. This giant 11 million cubic feet thing above me, I see, giant and round, goes by, and I see that, and then I'm stabilized out. And from that point on, I'm screaming toward Earth, slowly speeding up. And then, because of the way the spin system works, you end up doing this porpoising up and down, and we knew that was going to happen. But porpoising up and down is not bad. As you get faster and faster, your speed builds up. You break the speed of sound. You eventually get up to 822 miles an hour. And at that moment, you're going fast enough and the atmosphere is thick enough so you can start to hear the wind for the very first time, and then you start slowing down. And you're looking at your altimeter. You're looking at the beautiful views. You're trying to stay stable and on one heading. And you're waiting for 4 minutes and 27 seconds to go by. And so I get down to the pull altitude, and then it all turned out well.
Thank you so much for joining us today.
Oh, no, it was fun for me. Thank you very much.
We had more of a chance to talk to Alan, and we have posted those videos also on our Facebook page.
Now, we've learned about the layers of Earth's atmosphere, but do you all think that there are layers of atmosphere on other planets?
Yeah? Well, we have one of our astronomy educators, Shauna Edson, is with us today. Shauna, can you explain to them about the layers on other planets?
Yeah, there's some really cool stuff on other planets. It's really different from Earth, but the best place to show you that is actually at a different artifact. You guys want to come with me and see it? Yeah. All right, let's go.
Okay, I guess we'll clean this up.
Yeah, well,
Okay.
You guys go. We'll just, that's fine. Just take this.
Well,
Work like this?
So I brought you all the way through the museum to come look at the Vega spacecraft. We're familiar with the Earth's atmosphere because we breathe it. A planet that's really close to Earth that has a really different atmosphere is Venus. So this Vega spacecraft, this was built by the Russians, and they sent 2 of them to Venus, and they actually landed on the surface. Now, landing on the surface of Venus is really hard. What are some of the things about Venus that make it hard to land on the surface?
It's super hot.
It is really, really hot. The surface of Venus is about 900 degrees Fahrenheit. The other thing about Venus's atmosphere, it's really, really thick. It's got so much more atmosphere than the Earth that if you're standing on the surface, the pressure of the atmosphere above you is 91 times what it is on the Earth. So that is the same pressure as if you were 1 mile down under the Earth's ocean. Is there anything else you've heard about Venus's atmosphere that makes it kind of difficult to land on?
Winds.
There's winds, there's really strong winds, so it did get kind of blown around as it was dropping down to the surface. The other thing with the atmosphere is that it's got sulfuric acid in it. So the atmosphere is trying to crush, melt, and dissolve the spacecraft all at the same time. So it was just under an hour that it managed to get measurements and study the atmosphere and study the surface. So this spacecraft and the Venera spacecraft that were before it, those are the only pictures we have of the surface of Venus. When we look at Venus from space, what do we see?
Orange. Orange.
Orange, right? Can we see the mountains? No. Can we see the surface? No. We actually cannot see Venus's surface because the atmosphere is so thick. Now, there's some other cool stuff about the solar system, but I'm gonna have us sit down so we can talk about it a little bit more.
Thank you.
Yes, sit down.
If Venus's atmosphere is so thick, how did the sonar map the surface without seeing the having the atmosphere go in the way?
So the atmosphere of Venus and of any thick atmosphere planet, the particles and the gases block visible light. So our eyes can't see through it. But the radio light that radar uses is a longer wavelength. The atmosphere doesn't stop that. The radio waves get right through the atmosphere, they bounce off the surfaces of the volcanoes and landforms, and it comes right back. So when you're gonna try and look at a planet through an atmosphere, even at stars or anything in the universe, you wanna look at it in a whole bunch of different kinds of light, because you'll see different stuff. I love this. You guys have such awesome questions, but where are Marty and Beth? What are they up to?
Well, unfortunately, we are out of time for today. But our friends that joined us had some great questions, and we really appreciate them being here.
Now, if you have questions about the layers of the atmosphere, be sure to tune into Facebook Live on October 18th, and we'll answer all of your questions.
You can send them to us on Twitter, on Facebook, via email, carrier pigeon, however you want to get them to us, we will take them and get them answered on October 18th.
We also want to thank Shauna Edson, our astronomy educator, and our meteorologist, Chris Strong, who came out today.
We'd also like to thank the Eustace Kwan family for bringing this show to you today. Thanks for watching.
Layers of the atmosphere, scene 2, take 2.
The thing I said about going pro, scrap that.
Well,
work like this?